This is going to be the study guide for Unit 6. This unit is all about integration and accumulation of change, which means accumulation of change is about the area underneath the graph. As you go underneath the graph and are adding up that area, you're accumulating the change that is happening there. So that's what that vocab means. This is the first unit where we have a few topics that are from just BC material. So if you're planning to take the AB test, there's a few sections that I've highlighted in red that you don't need to worry about if you're taking the AB test. But if you are taking the BC test, you'll need to know all of these things here. So the first thing in Unit 6, we're talking about applications of integration. And the very basic application of integration is finding the area underneath the curve. And so to first understand what an integral is, we have to understand how to approximate that integral, how to approximate that area. And so the first four sections here are talking about Riemann sums. So the area, approximating the area using rectangles or a trapezoid. So I've already filled in the formulas, I guess, for each of these. This is just a general graph, arbitrary graph, as well as a table. You could see it in either form, a table or a graph, and interpreting it from that. If you noticed here, I've marked these arbitrary x values on the x-axis here. And if you go through each of the sums, I'll explain each of them, you'll see that they're all pretty similar, except the x values might be a little bit different. So for a right-hand Riemann sum, in general, what we're doing is we're looking at all of our intervals here from x1 to x5 for this arbitrary graph, if we're being asked to approximate the area of this integral from x1 to x5. So you'll notice each integral here, x1 to x5, that's the bounds. And I put approximation equals signs here, the little squiggly equals signs, because that's indicating that I'm approximating the integral, meaning I'm approximating the area under the graph. So a right-hand Riemann sum is you start from your first interval, and right-hand means you take the right endpoint of each interval. So I find the right endpoint here, this first one, first interval, which is x2. Now, I'm using a rectangle to approximate the area under the graph. So the height of this first rectangle using a right-hand Riemann sum uses the right endpoint of each interval, and you go up to the height of the function at that point. And the right-hand side, you go up, and then you go draw your rectangle like that. And so if I go throughout this graph and use the right endpoint of each interval, that means I'm using x2 for the first interval, x3 for the second interval, x4 for the third interval, and x5 for the fourth interval. We have four rectangles here. So we did not use the height of x1. So if you look at this integral, or this approximation here, we started with f of x2 as the first height times the base of that rectangle, which is x2 minus x1. This is the base times the height. So base times height, f of x2. And if it's giving you a table, you just pull the value from the table and replace it here. So this might look like a lot, but when you do an actual problem, which I will do, I'll follow this up with some more free response problems that use Riemann sums. This should be a pretty quick calculation to do. It's just multiplying and adding up the terms. So then you'd go on and multiply the base and the height for the next rectangle, so on and so forth. So what you see right here, this is the right-hand Riemann sum, because I use the right endpoints of each interval. If I use the left endpoint of each interval, your rectangles will look different, because I would be starting at x1, drawing my rectangle down there. And I would use x2 as my next height, so on and so forth. And so you can go through and look at the rest of these. The midpoint gets a little tricky because you're going to skip points. Basically with the midpoint, you find your intervals, and it'll tell you how many sub-intervals it wants you to use. So for this midpoint Riemann sum, since there are x1, x2, x3, x4, and x5, and I only know these coordinates here, I would only be asked to use two sub-intervals because I need to use the midpoint of each interval. So x1 to x3, the midpoint is x2. So that's why I start at x2 right here, f of x2 as the height of the rectangle. So for a midpoint Riemann sum, I would draw my line going across the midpoint y-coordinate, and then for the second interval, x3 to x5, I would draw it going through this coordinate right here. So that only allows me to do two rectangles. So midpoint depends on which problem, what the problem is giving you. And then trapezoidal Riemann sum, the area of a trapezoid is 1/2 base 1 plus base 2 times the height. So if you see in my terms here, I have 1/2 base 1 plus base 2 times the height. Now the height of each trapezoid is the difference between your x values. So don't get it confused with the height this way. This is actually the base of each trapezoid, because if I draw a trapezoid using x1 and x2 right there, and I connect those, you have this trapezoid, but it's placed on it's like kind of standing upright. So in this case, this is base 1, this is base 2, and that distance is f of x1 plus f of x2, 1/2 times that, and then multiplied by the height or the distance between the x values here. So that's the trapezoid rule in short. I will try my best to find one of each of these, a free response for one of each of these, or an example with one of each of these, so you can see how each one has worked in an actual problem. Okay, you can pause it right here and copy it down. I'll also post this completed key here, so you can also take your time and copy it down. In this unit, we also talk about the different methods of integrating, other than just basic integration of, doing the reverse power rule. We do have U substitution, and then integration by parts as well. So these three topics here, I've written BC only. So right now, if you're taking the AB test, you don't have to worry about these three. Just focus on reviewing U substitution. But for integration by parts, we have our formula here that we used before. So I'm not going to put too much in these boxes because integration is really kind of complex topic which can only be shown through examples. So I'll do that in a different video. But here's our little ladder on how we pick u and dv. And when we set up u and dv, we derive u and we integrate dv. And we replace those terms back into this right here, uv minus integral of v du. Okay, and then this little ladder islate right here will help you pick what is supposed to be u and what is supposed to be dv. Integration by partial fractions, this is probably the most that I can put in this box, just so you know how to recognize partial fractions if it does show up. We usually have some constant over a polynomial that can be factored into two different factors, and you have to figure out what a and b are. And we use the Heaviside method, which you cover up one of the terms, and then you plug in the solution to the factor into the other term, and try to figure out these constants a and b up here, and then you integrate the two terms separately. Improper integrals, the easiest way to recognize that is you see a bound is infinity. Rarely you might see one of the undefined point is in between the two bounds of integration. Okay, so I'm going to go back up to first and second fundamental theorem of calculus, because those do show up quite a bit and are free. Like, I would be surprised if they didn't have this on the AP test. It's literally called the fundamental theorem of calculus, so I don't know why they wouldn't test you on it. The first fundamental theorem of calculus essentially says that if I take an integral from some value a to b of this function, arbitrary function f of x dx, it is equal to its antiderivative evaluated at b subtracted by the function its antiderivative evaluated at a. What I'm going to do here, though, is I'm going to put f prime here so you kind of understand this. This is more commonly seen in free response problems. So I'll put f prime here. If you're integrating f prime, you get back up to your original function, f of x. And when I evaluate, I do f of b minus f of a. The antiderivative with b and a plugged in, and you subtract. Okay. Now a common application of this that you'll use on the AP test is you'll see this equation rearranged, meaning one of these guys will be isolated. So for example, I can rewrite this equation and make it f of b is equal to the integral from a to b of f prime of x dx. And since I isolated f of b, that means that I would have added f of a to the other side of this equation. So I have plus f of a here. So these two equations are equivalent to each other. They're just kind of reshuffled, reorganized, rearranged with the terms. So a common free response part might ask you to find f of something. Like, for example, find f of some value. And all you have is a graph of the derivative, and you have some other point. So you can use the area under the curve of the derivative, and you can use that coordinate f of a to figure out what f of b is, because you know this holds true right here, so that means that this must also hold true. These two equations are the same exact thing, they're just reorganized. So there are many problems like this that have this exact equation or this exact idea used. Okay, let's move on to the second fundamental theorem of calculus. This is also pretty commonly used or applied. The way you recognize this one is if you have some constant for your lower bound and you have a function g of x as your upper bound. Yeah, I'll leave it as g of x because it could be like x squared as the upper bound, or 2x to the power of 3, something like that. I'll put an example of that though. And then we have our function, some arbitrary f of x dx. So now what this is saying is, what the second fundamental theorem of calculus says is if I derive this entire integral, I'm going to apply the derivative operator right there. That means d dx means take the derivative of this stuff inside the brackets. Well, then the second fundamental theorem says that if my lower bound is a constant, all I have to do to derive this whole thing right here is, since I'm deriving an integral, I'm essentially preserving f of x right here. And all I'm doing is dropping this, whatever this upper bound is, into here. And this upper bound is not a constant. This upper bound is something in terms of x. So that guy gets dropped inside of here. So I'm going to write f of g of x right here, because g of x gets dropped into what f of x is. And if g of x is something in terms of x, we need to apply the chain rule here. So we need to apply a g prime of x right here. And this is what the second fundamental theorem of calculus is. And just real quick, while I'm in the middle of this video, I'll just show you an example so it's a little bit more clear. Let's say I had the integral from 1 to x squared, and let's say my function was sine of x dx. Okay, this is just an example. And I'm asked to derive this guy. The derivative is going to be, this guy is preserved. The sign is preserved because I'm deriving an integral. My lower bound is a constant, so now this indicates to me this is the second fundamental theorem of calculus. I'm going to drop x squared into sine. So this would become sine of the x squared dropped into there. And then I would multiply by the derivative of x squared. So I would multiply by 2x. And that's the derivative right there. Okay? I just want to show you in parallel how this would look in an actual example. Okay? You don't need to actually put that example on here. That might confuse you more. Just leave it in general so you know how to identify when the second fundamental theorem of calculus will show up here on the AP test, if it does show up. Okay, so I'll leave this right here. You can pause it and then copy it down at your own pace. I'll also follow this up with as many free response parts as I can in separate videos, just so that you can see all of these things in context of an AP free response problem, so you know when to identify when you need to use each of these.